Hi everybody, so this is a video that was requested last week, but I'm getting around to it this week. I apologize. It's that this one, number 68, which says a satellite in geosynchronous circular orbit is 42,164 kilometers. From the center of the Earth, a small asteroid collides with the satellite, sending it into an elliptical orbit of apogee 45,000 kilometers. So what is the speed of the satellite at apogee? Assume the angular momentum is conserved. Sure. So a couple terms here that you may not have heard, but if you just do a quick Google search, you'll be able to find out what they mean. So first off is geosynchronous orbit. That basically means that if I was standing on the Earth and the Earth was like, if I was standing on the equator and the Earth orbited around like that, the satellite would orbit exactly above my head no matter where I went, right? That's what geosynchronous orbit means. So yeah, before we get into this, let me just look at, well, I can find out then what the period is of geosynchronous orbit, and that's one of the reasons that they brought it up to me, is the period then would be, 24 hours, right? Because it takes 24 hours for anything in geosynchronous orbit to orbit around once, because that's the amount of time it takes the Earth to orbit around once. So this is going to be 24 hours, but we always want to try and convert that into seconds. So 1 hour is 3,600 seconds. So 24 times 3,600. That's going to be 86,400. 86,400 seconds. All right. So, and that's going to be useful to me. I also drew that initial radius there of 42,164. Kilometers is times 10 to the 3 meters. So that's why I just added it there, right there. Okay. And then the other thing I want to try and figure out now is then, if that's the period, what's the angular velocity? And remember, angular velocity is the amount of radians, so it'd be 2 pi radians divided by the period, which was 86,400. And I'm just going to leave it at that because I don't want to get, I don't want to make, I'm going to leave it at that and then I'll plug things in later. So that's omega 1. That's the angular velocity of this satellite as it orbits around. So it goes 2 pi radians in 86,400 seconds. That's the idea there. And what they're basically saying in this problem is that an asteroid then shows up and knocks it into a different, kind of in a different apogee, right? So it knocks it, and so it does it so it's no longer going in a perfectly circular motion. It's now going into this warped shape here. So, and then this we call, again, you could Google this. This is called the apogee. I think that's how you spell it. And this one, I forget even what that one's called now. I think it's like pedigree or something like that. It really doesn't, doesn't matter to me too much because, again, it's just something you can Google and look up. So this then I'll call R2. And what they're saying here is basically assume that the angular momentum is conserved. So here I'll say, here's the first angular momentum. So that's going to be equal to I1 omega 1. And then when it goes over here, right, you can see the moment of inertia is going to increase for this object because the mass is further away from the axis of rotation. This is the axis of rotation here. So this is going to be L2, which is I2 omega 2. And they're saying assume the angular momentum is conserved. Sure, let's do it. So the angular momentum at 1 is going to equal the angular momentum at 2. So that means I1 omega 1 is equal to I2 omega 2. So another thing is what I call this. So this is a mass that's distributed far away from the axis of rotation. So I'm just going to call it a point mass. And the moment of inertia of a point mass is just mr squared, right? The mass, the point mass itself, multiplied by its distance from the axis of rotation squared. So this is going to be m1 r1 squared omega 1 equals m2 r2 r2 squared omega 2. And then m1, well, the masses are the same. So those masses are going to cancel out. So I'm left now with, let's see, I'll isolate omega 2. So this is going to be R1 squared divided by R2 squared. Omega 1 equals omega 2. And lastly, they want the speed. And this is something I kind of screwed up. Sorry, when I wrote my answers, I just found omega 2. But they want the speed. So a way I can get to that is that I can remember, well, the speed, V2, would be R2 times omega 2. So it's kind of that relationship translating between rotational velocity and linear velocity. So I'll use that, or rather V2 over R2 is equal to omega 2. So I'm going to use that and plug that in here. So I can replace that. So this is going to be R1 squared over R2 squared. Omega 1 equals, this is V2 over R2. And then I can see one of the R2s is going to cancel here and here. Almost done. So now I really just need to plug everything in. R2 is over here. They told me at the apogee it's 45,000 kilometers. So that means R2, let's make this a different color here. Let's do it in blue. So this is R2 is going to be 45,000 times 10 to the 3 meters. All right. So this first one was 42,000. It was 42,164 times 10 to the 3. Or yeah, 42,164. Wait, is that right? Yeah, times 10 to the 3 meters squared divided by R2, which is 45,000 times 10 to the 3. And then multiplied by omega 1, which we found out was all this mess right here. 2 pi divided by 86,400. All right, so and that's V2. So that's a bunch of nonsense, but I can plug that into my calculator. Shouldn't be too big of an issue. So I got 42,164 times 10 to the 3 squared divided by 45,000 times 10 to the 3, and that's it. So that's something, but I'm going to carry that over, multiply that by 2 pi, and then divide all that by 86,400, and I get about 2,873 meters per second. So 2,873 meters per second. And there we go. So that would be the speed right there. So again, a couple of terms I had to Google and look up, and you're free to do that as well. So geosynchronous orbit as well. But really, this is a conservation of angular momentum problem with a lot of hidden assumptions in here, right? A lot of just, like you had to remember, how to get the period. So if you know what a geosynchronous orbit is, you can get all that. Well, yeah. So hopefully that helped. All right. See you guys. Bye.